All right, folks, welcome again. We are going to go over the solutions to the homework. Just to recap what was the homework we left with last time, we were getting started with training and fine-tuning of models. So as a refresher, we wanted to go over the basics. How would you take, for example, a PyTorch, and how would you use PyTorch to write some, just from the ground up, some basic classifiers and regressors? Remember, these were supposed to be warm-up exercises. Most of us know how to use PyTorch, and the idea was that it would provide a basis to quickly ramp up, get your hit the ground running as we entered fine-tuning. So there are three levels at which you can train the model, three sort of API architectures you could use. You could use the low-level PyTorch itself, write code in PyTorch, which I strongly advise you to do. Of course, you can go one tier lower if you are like daring and adventurous. And it's a typical thing that you give in college as an exercise. You say, don't use any library, just use NumPy and so forth. And from scratch, implement a neural network. And with that neural network, solve these problems. Actually, the problems that I gave, all of them were solvable without using PyTorch at all. You could easily do it in NumPy in a short amount of time. With that being said, nevertheless, we decided that we'll use the simple exercises to brush up on our PyTorch understanding. So the problems that I gave were classifier models, a model to detect if there is a negative number present in a set of 10 numbers as input, output the result as a probability and also a label such as true, false. This was the first one. The second one was, again, hang on. Okay. A model to predict if the sum of the input numbers, 10 of these, add up to greater than 100. Once again, output a probability and a label. A model to find the maximum in a set of 10 numbers as input. By the way, this I'd accidentally put it in the classifier into the regression section. You can do it as a regressor, but it's much more natural to do it as a classifier problem. Then as a stretch goal, I'd given a model to detect the presence of a prime number in a set of 10 numbers given. Now, regression, the problems were a model to find the sum of inputs, which is very much related to part B of the classifier problem. A model to find the standard deviation of the inputs, 10 numbers as inputs. And as a stretch goal, which I actually didn't announce in the class, but later on I added to the portal, was that a model to output the factorial of an input number, assuming that the number is relatively small, not a big number. In order to train these networks, you'll have to do a careful generation of training data. So most of you would have had to do that. So given the fact that these were that, I would like to know, first of all, congratulations to the ones who did solve all of these problems. It is good. I think as we have gone from LLM 1 to LLM 2, I do. Please mute yourself. I do notice that people are losing a bit of steam. Please don't do that. We are getting into very, very interesting territory. In particular, we are going to move on. Fine-tuning is what makes a language model, any language model that you train, into something like a chat GPT. So this topic is of paramount importance. We are going to move from big topics to big topics now. With this foundation, we're going to go into code generation. I know some people have really been waiting to see how can you generate code using large language models? How can you generate SQL? How can you generate HTML or whatever it is? How do code generators work? That's a big topic coming up. And it is all related to the fine-tuning that we're going to talk about. We are, can you guys please stay muted? Yeah. We are also going to, after that, go into one of the hottest topics today, that is causing, that's sort of the foundational to a lot of breakthroughs that are emerging, the graph neural networks. And we'll see how transformers, what's the role of transformers in these language models in the context of graph neural networks, what role they play, how does it help detect outliers. And as some of you know, today, graph neural networks are foundational to the new recommender systems and many, many things that are happening, the state of the art, molecule, drug discovery, and whatnot. There are many, many things that are coming thanks to this. Okay, I'm getting a call from a student. Hello?
Grasshopper, call for extension 0 to accept. Press
Excuse
1
me 1 second.
to send the.
Hello, this is Asif here.
Hi, this is Priya.
I'm giving a lecture. Can I call you back later?
Oh, sure.
Yeah.
Bye.
All right, so we are going to cover that, and then we'll circle back to the main topic. In this course, one of the primary things I wanted to cover are multi-agents. These are big things that are happening today. Looking at agents and assistants and how interplay of multiple agents can lead to very powerful and robust applications. It's one of the core themes of this particular bootcamp. So I give you guys a starter. We started with Autogen. Is there anyone who tried and played with Autogen? Okay, guys, we are falling behind. And see, I can keep on releasing solutions, but if all we do is read solutions, that is not terribly useful. Speaking of solutions, I've released, by the way, other than Autogen, all the solutions are online now, right? So in particular, your textbook builder is online. Your whatever the code that I ran through last week is online, and I'll show all of those things to you. But guys, I have been hesitant releasing solution because one basic rule is you release solution when at least half the class has done the homework. I'm having a little bit of a difficulty with our current batch reaching that. In particular, for example, this homework is the same homework that I gave to the Tuesday batch, which is the absolute introductory batch. To their great credit, I have been busy grading because people have submitted their solutions to me through the portal. I have been grading those submissions, and I have almost a large number of submissions. But for some reason, here we are the more advanced class here. You have all gone through a lot of training by now, LLM 1 and many courses. I have barely any submission. So I could obviously continue to release solutions as we go along. It may not be the most educationally the best approach to do, but I don't see any other option. So I will continue to just keep releasing solutions with maybe 1 week of pause, right, at most. So I realize that some of you are very, very busy, and there are people in the audience who are just sort of waiting for the solution, thinking that is high value, they're too busy. But for those of you who do have the time to solve the problems, please put in the effort to solve it. Don't look at the solution. The best that I can advise you is, even though I'll release the solutions early, don't look at the solution, try it on your own. And if you can't, then take a peek at it. Right. So, all right, this particular homework we'll walk through it in the morning. In the afternoon, here's a plan for the day. We are going to go completely into fine tuning. Now, as I said, there are 3 levels at which you can fine tune a model. You can fine tune a model using just Pytorch itself, because fine tuning is nothing but training. What's the difference between fine tuning and training? There is no difference, right? To train a model which has already been trained before is to fine tune it. Can you fine tune a fine tuned model? You can go on fine tuning a fine tuned model. You can take a fine tuned model and further fine tune it. I'm answering some of the questions that people have asked. Can you apply, is it a RAG versus fine tuning? Why do I need to fine tune if I have RAG, for example, retrieval augmented generation? Who would like to answer that question? Is it really
Yeah,
worth?
we talked about the distribution, right? If the domain, the data distribution is completely different, then fine tuning makes sense. Otherwise, we can live with the RAG.
Yes. Yeah, excellent. Thank you, Christian, for mentioning that. And the reasons to fine tune, nevertheless, even if you're doing RAG, this is not a this versus that, but it is you can do both in the same project. The reasons in favor of RAG is the reasons when you don't want to fine tune a model is when you are dealing with a very proprietary data and you don't want the model to learn from that data. Because if it learns, we talked about it, a model is like a child. You can easily have the child tell you whatever it knows. Right? So it's dangerous. So there are issues associated with that aspect of it. On the other hand, of course, some of these are theoretical issues because if your model is behind, is only within intranet, is never exposed to the extranet, etc., then the point becomes moot. You can actually fine tune it on your proprietary data and still use it. But the reason that is unavoidable, where you have to fine tune, is if your data has a distribution that is at variance or that departs significantly from the data distribution, statistical distribution of the training data. In that case, you have to fine tune. For example, the word like to short has an entirely different meaning in common parlance than in finance. The sentiment associated with a bear and bull are entirely different in finance than would be associated with that, right? And a similar thing that Sukhpal here will appreciate, that if you have a patient and you say there was no remarkable findings in a lab result, that is usually considered a very good result, not a very good thing. It means that the patient is completely healthy, because any finding worth remarking usually for a physician means there's something wrong, right? But that is at complete variance with the way that common people talk, right? And every domain has its private language. It's almost like a shibboleth to encode or to communicate things between professionals, in a way avoiding or being too noticed by offending the general public. So, for example, it has become in recent parlance, I noticed in various physicians, if you go for a lab test and you're overweight, they will call you in the note somewhere. It will be mentioned this was a difficult study. The difficult study simply means that you were overweight, and you wouldn't know that, right? So that's how it goes. So what happened? The reason to do, therefore, to do fine tuning where it is absolutely necessary is when you have a distribution. So as you can see in this particular case, the linguistic distribution is different. The words mean different things. It's the same word, but they're like homonyms. Difficult. You would not typically associate a difficult case with a fat person, but or very overweight or obese person. But that's what it becomes in medical terminology, right? And so you need to do fine tuning. That's a case for it. Now, while I started with that, the second biggest reasons to fine tune, and so that is fine tuning. But I'll come today to the most significant reason that has brought fine tuning to the forefront. I was keeping it for this time, and now we'll have the point. And it's an open secret. We all know about it, but I'll talk about it. So there are three ways that you can fine tune. You can fine tune using Pytorch, which is just basically saying, okay, let's run the same training loop. Do you remember the training loop? What was the training loop? For n number of epochs, go to that data, treat the data as a sandhill, take scoops of the data that you call mini batch, right? Do the forward pass to the model, compute the loss. So when you do the forward pass, you will get the predictions, the y hat. From y and y hat, the ground truth in the y hat, you now come to a loss function. Your loss function, for example, for classification, your loss function could be a binary cross entropy loss, a measure of surprise, You expected it to say something. Let's say you expected it to predict that this thing is a cat, but it is saying the probability of cat is 0.1. That's hugely surprising. The model isn't doing well. So cross entropy is just a measure of surprise, knowing the label. So that's your loss. You need to mitigate that loss. You need to bring up the probability that it's a cat. As simple as that. And so for that, what do you need to do? You need to do gradient descent, but you can't do gradient descent till you have computed the gradient. So the first step is to compute the gradient in the last layer, then to backwards, do back propagation of it. Once you have back propagated all the gradients throughout the network, then you take one step of learning. In coordination, every single weight in the system is updated to its new weight by doing W minus learning rate times the gradient of the loss with respect to that weight. Right? So that is it. And so, and the code, as we walk through the code, literally is that thinking writ large. The inner loop of that was for every epoch, for every mini batch, given a mini batch, you take the forward journey, you compute the loss from the predictions, you do from the loss, you do a gradient and back propagation of the gradients, and then you take a step. Isn't it? Literally 4 lines of code. That is the 4 core lines, the inner loop of all learning in machine learning in some sense, especially with, particularly in the context of neural networks. In the context of non-neural networks, of course, you don't have backpropagation, right? You just have the gradient descent step, one way or the other. So that is that. Now, we also talked about that gradient descent, the way we have talked about it is sort of a simplistic way. There are many, many optimizers. Many of you have been through my courses, and you know that back when I say gradient descent, I don't necessarily mean the vanilla simplistic gradient descent, which for many batches actually is highly unstable. It's a sort of a stochastic gradient. It's not very effective, but to stabilize it and to make it more well-behaved, there's a whole theory of optimizers. And you do momentum-based gradient descents, and there's all of these families of gradients. So one common rule is that just use Adam W from a practical perspective as a baseline. If you don't know any better, just start with Adam W. Don't start with batch gradient descent or stochastic gradient descent. Generally, you're much more likely to have unstable results. And I think some of you report, well, in this particular batch, nobody did their homework except Yashila and Prakash Ranade here. But in the other batches, people did it, and they reported that, for example, if they use SGD, their losses were blowing up completely for some of the problems. Right? So again, goes to show that sometimes just by changing the optimizer, you get much better, more well-behaved answers.
I was told in college that if we had like losses that blew up like completely, like very unstable learning rates that were like very unstable gradient descents, that we're supposed to decrease the learning rate so that we would essentially force the optimizer to take smaller steps. Like, I know that that's probably not as effective as improving the optimizer, but all else failing, there are other ways to.
That's a very good topic, Yashila, and I'd like to dwell on that. Thank you for bringing it up. I was going to sort of breeze past it because we have so much to cover today. But since you did bring it up, let me elaborate on the details. See, you have 2 degrees of freedom. You can play with the learning rate, which is, and the technology is the learning rate scheduler, LR scheduler. And the other is obviously which optimizer you're using, whether you're using momentum or not, and so on and so forth. So which of these 2 methods to use to bring down is a nuanced problem. And often you get intuition by staring at the problem. So I'll tell you how it goes. See, when you use a learning rate scheduler, what it says is that for one sort of a step, one journey, I'm going to set the learning rate to something. When you use an optimizer, let's say momentum-based optimizer. What is momentum-based optimizer? The basic intuition of a momentum-based optimizer is that you keep a moving average. So think of stock fluctuation. The stock keeps fluctuating. So what happens is when you do normal gradient descent, maybe I should, this is an excellent thing when I should just write it out to show what I mean by that. when you do, let me take a new page. And please bear with me as I pull through the writing pad. So nice, Sheila, you sort of stalked me. I wasn't sure how many people would be interested. So here's the big deal. See, when you do stochastic gradient descent, you have a batch, mini batch. Now, given the underlying assumption, which is almost always true, data is never clean. So given a pile of sand that you took from a big heap of sand heap. So this is your mini batch. In this mini batch, and we'll use a metaphorical language, what happens is that there is information plus noise. Right? It comes with every data point has noise. It is never exactly capturing the relationship between the input and the output of what the unknown function could be. So just to recap, see, the point is that you're trying to find out, let's say that this is the unknown truth, unknown force producing ground truth y from x. You'll never know f. What is our goal? Our goal is to produce y hat is equal to g of x, where g effectively is an approximation to f. So it's sort of a universe, it's an approximator of f for all practical purposes, right? So some function that you want to do. Now, for it to do that, you have to trust that the x that you got was well measured and is correct, and the y that you got is also correct. But in reality, it will have noise. And also, the loss landscape that you will have will be, as we saw the picture of a loss landscape, it is not, it will be like this. So there is a minima, but there are a lot of other areas that you can get stuck in. Right? So because you can get stuck in local minimas, and because of the noise in the data, your path towards a goal, let's say that this is your minima. This is your parameter, the best parameter point, and you start here. You are zigzagging your way like this towards this, right? And the thing is, you may keep zigzagging around it in a standard gradient descent, mini batch gradient descent. Now, this picture, if you look at it, it looks sort of like the way the stock market behaves. And if you notice in finance, what do people do? Anybody who's dealing with time series, they tend to look at the slow moving average. They'll say, what is the moving average? Isn't it? So what is the moving average? Is the average of a small window, the last window of so many records. Moving average. And so this actually agrees with the physical notion of a momentum. And what you're basically saying is that suppose I have a momentum in this direction. And at this point, the gradient points in this direction. Right? This is the momentum. This is where the P is, momentum is, or a moving average vector is pointing me in this direction. And here is the gradient of the function, gradient of the loss pointing. Should I go up? Should I go in the direction? So let's call that the direction A and the direction B. P is asking you, the moving average is saying, ignore the gradient. Let's stay the course. Let's go to A. Whereas the gradient is telling you at this point, no. Let's go towards B. Right? And you do know that because the gradient is computed on a mini batch, it has errors, but it does have information. You want to learn from it a little bit, but you also want to respect the fact that the history, the momentum, which is built out of the history of all the past batches, what they are pointing to is also meaningful. So what you do is you take a proportion of this. You take, and I think P plus 1 minus P of the gradient, or you can 1 minus alpha of the gradient of the loss. Right? So some proportion, let's say you can say 0.3, 0.7. Well, the numbers are actually, I'm giving a very simplistic explanation. when you actually look at Adam, there are proportionality constants, there's sort of mechanics associated with it. But the basic intuition is you listen a little bit to the history, to the momentum, and you listen a little bit to the gradient. You don't completely swing to one side. Does that make sense? Right. So what that leads to is it leads to a less erratic movement. It just sort of leads to a more smooth, or theoretically at least, you have a much more controlled progression towards this. But then the other aspect that comes in is the learning rate. But before we go to the learning rate, what does momentum give you? As you can imagine that you're this little ball. So when you come here, what is happening here? Think about it this point, guys. At this point, what is the gradient? If you're coming down this slope, what is the gradient at the bottom of it? Say that?
Is it close to 0?
0, right? Gradient in this one dimension is just a slope. There is no slope. You're bottoming out in that valley. So gradient is 0, right? So if you only listen to the gradient, you would stop there. You would stop at a local minimum. But because you have the momentum term, it is pushing you to continue forward. And so you end up popping out of that local minimum and continuing your journey. You see that, right? You continue your journey, and then a similar thing hopefully happens here, and you continue your journey, right, towards your global minimum, which is why you should always use a momentum-based, one of the momentum-based optimizers. Now, momentum-based optimizers, right? The amount of learning they do, or the amount of correction to weight. See, ultimately, what is changing? The weight is changing to W prime to W delta prime, etc., etc. This is sensitive to every mini batch, because every mini batch brings its own loss, gradient of the loss, isn't it? On the other hand, there is this one thing that is sitting there, which is that minus alpha, gradient of the loss. You remember that? And in a simplistic view, we always took this to be constant. But actually, what happens is you don't want to do that. One analogy that I'll give you is when your plane is landing, or your train is approaching a station, or a bus is approaching a station, it doesn't move at the same speed and then put absolute full brakes the moment it reaches a station. Right? What vehicles do is that when they are far from the destination, they are moving pretty fast because they're comfortable in the knowledge that they are still pretty far from the destination. Right? But as they come closer and closer to the destination, they begin to slow down, isn't it? For example, an airplane typically will cruise at 500 miles an hour. Right? And typical jet propelled airplane will go at 500 miles an hour. But when it is landing, and one of you may correct me with a flying experience, my own experience of being in the seat taking off is more than 30 years old now. But and obviously I never flew a big commercial jet. It was little twins, but you come down even in a commercial jet, you're coming down at nothing more than about 70 miles an hour or so. Right? You hit the runway at a fairly low speed, and then you start breaking down significantly. Why is it? Because you don't want to overshoot. At high speed, it's hard to control, and you'll overspeed. So what you need to do in the similar way is that it is all right to move fast, learning rate to be big in the beginning, but eventually you want to keep slowing down. So what you do is every epoch that you run, or every step, depending upon how you do that, you can cycle through, you can do a learning rate scheduling. You can schedule your learning rate and say, hey, let's do it like this. The simplest learning rate you can do is, you can say, well, of course, the fixed learning rate, the constant learning rate, constant LR is easy. your alpha is constant. This is implicitly what you do when you don't do anything. Another learning rate, which is fairly popular, is you go like this. Your learning rate keeps decreasing, and so on and so forth. Right? Another learning rate is you go like this. Another learning rate that's fairly popular, and again, there are many, many variations people have come up with, is exponentially decaying learning rate. Right? Another learning rate you could have is, I'm running out of colors now. Let me see if I can bring in another color. Another learning rate could be like this. Right? Another learning rate is cyclic, actually. Let me remember how it is. I believe it is like this. Sorry, it is not like this. Sorry. It is, you decrease and then you jump up, you decrease again, you jump up. Cyclic. So there are many schedules for the learning rate. These are, so alpha therefore becomes a function of steps. Are we together? How many steps you have taken? It becomes a continuous function of the steps. Oh, sorry, I shouldn't use the word f because we use the f for the function that you're approximating. Let me just use, what should we use? Let's just say it is some function chi of steps. Right. And these are all possible things. You call it the scheduler. The reason you call it the scheduler is in the parlance that we do of training models, you often think of steps as time because the next step will happen in the future. So in some sense, the steps become synonymous with time. And so the learning rate varies with time. Typically, you're controlling it with time, and therefore people often use the word scheduler, learning rate scheduler. Right? I'm just guessing it at this one. That's the intuition that at least I carry in my mind of why it's called. Yeah.
Krishnan had his hand up. I think he had a question, if I'm not wrong.
Oh, yeah, sorry. Thank you. So I think, as we explained, but I was thinking on example, when we pay the gas station like a fixed amount, $50, right? And when the time comes to 45, then it slows down. So I was thinking that as an example for
exactly. That's a very good example, actually. It's a very, very good example.
Okay.
I have one question, Asif. What is the intuition for stochastic gradient descent versus the standard gradient descent? Like what type of intuition that we should carry, in terms of deciding which one what?
Okay, so we are revisiting gradient descents a little bit, but let me do that. See, gradient descent is the basic gradient descent is, suppose you have this much data. This is the whole amount of data. Let the data set be D, right? If D is the data set and you compute the loss, so you do the forward in Python, in Pytorch language, you do the forward journey on the D itself, right? Or more mathematically, if you do D itself to compute your Y hat, the entire data set, one step, and then you compute your loss on the entire data set, right? For every point. So what happens is that for every point, in reality, this should be written as xi, and xi belonging to the entire data set, one step. In one step, you do this, and your loss is a summation over the entire data set to compute the full loss in that step. And then when you take the gradient descent of that is taking what you would call batch gradient descent. It represents one extreme position. The other extreme position is you say, hey, forget about this summation. So this is one extreme position. Let me call it North Pole. The South Pole of this way of looking at it is, you say, forget this summation altogether. This summation, forget it. We are going to learn from one data at a time. So one step is learn from one data point. One data point, right? So you would just have that one data point is equal to fxi, and loss, there is no summation. Loss is just the loss on that particular data point, yi hat. You compute that, and you take the gradient of this particular loss on the single data point, right? Are we together? Now, this is, I would call, the South Pole of how gradient descents work. Now, what are the pros and cons of each of them? The pros of batches, well, when you compute your loss, your predictions over the entire data set, and when you compute its gradients, first of all, the loss that you take, some of the noise gets suppressed. You realize that, right? They will cancel each other out. The law of large numbers comes in, right? And because the law of large number comes in, then your gradient will be much more reflective on where you should really go, right? While in theory, that's true. And so you will often see that the batch gradient descent paths are oftentimes, not always, smoother. Obviously, batch gradient descent, the way you're doing it, it leaves no place for momentum. It doesn't leave place for anything else, because I mean, it does, but it's a little bit of a clutch. So it is what you have to wait a long time. The con is that you have to wait a long time to just see what is your loss after one epoch, right? One round through the data, because it has to compute all the values. It has to compute the gradient. It has to compute the loss across all the points. Then it has to compute the gradient of it, and then backprop it. Backprop and then compute the gradient and take a step. So one step means one journey through the whole data set. If your data set is billions of points or hundreds of millions of points, you have to wait a very, very long time to get to one step of learning. Right?
So in this case, Asif, if we were to think what machine is doing behind the scenes, so it's basically representing the W naught plus W1x1. So it's kind of calculating and building that function for each one of this learning. Is that how we
right? Because see, what is the next thing you do? The moment you compute the loss, you just do the W is W minus alpha, but alpha, now that we know, it's a learning rate scheduler controlled object, but you do one step of learning. So are you learning from every data point individually, or are you learning from the entire data set in one go, one step, right? So is your one step through the whole data? It is batch gradient descent. If your one step is through one data point, then your epoch is made up of as many steps as there are data points. Right? So these are the two extremes. Between these two extremes is the in-between position of, which is much more practical and almost universally used, of mini batch. This is the Goldilocks region, mini batch gradient descent. A mini batch gradient descent just says, take little piles of sand, take small mini batches of data, compute the loss across not the whole data set, but when you compute the loss, compute it sum over I belongs to a mini batch, belongs to a mini batch of data. And then you compute the total loss, and then you take the gradient, and then you do the W minus alpha, gradient of loss. So mini batch. But even when you do mini batch, the problem with mini batch is that you still sort of oscillate quite a bit. Right. And of course, you have the risk of being stuck in local minima. And that is where you bring in momentum. Right. So then you bring in the momentum based. So you don't actually listen to this. You actually replace this with this term in the momentum based. You replaced it with a different quantity, gradient t, which is partly coming from, let me just call it theta plus 1 minus theta of the actual loss gradient, right? Actual loss gradient. Right? So you listen to the actual loss gradient a little bit, and you listen to the moving average or the momentum that you have gathered so far a little bit. Right? And I would actually invite you at this stage to read this Inside Deep Learning textbook that I recommended on the course portal. It has perhaps one of the best illustrations using lovely pictures that I have seen of the different varieties of gradient descent. So please read that chapter on learning rate scheduler and gradient descent in the Inside Deep Learning textbook. It's beautifully done. It must have taken the author quite some effort to illustrate it in such a nice way. So I would strongly encourage you to pick from that. So that is the relationship. So remember that that's the relationship between the learning rate scheduler, which is a bigger step we should take, and the actual gradient descent methodology that you use. Today, we take it as a fact that you should always use momentum-based gradient descent in mini batch, or at least that's the default with which I start, unless I have a reason not to. Right? So I start with, and therefore my statement that I made before we went down this rabbit, namely use Adam W.
So as if the first step that we take mostly for all problems would be, like for most of the problems would be momentum plus mini gradient, the stochastic gradient descent plus
That's right. Mini batch gradient descent. So if you remember, the code that we went through last week was for epochs in, like for n epochs, for each mini batch, do the inner loop, right? So forward journey, like y hat is equal to the forward of the x, loss, compute, a gradient of the loss, and then backprop, gradient, backprop the gradients, and then step. Literally Pytorch API literally enumerates it as these lines of code, right? Loss. If you look at your inner loop that we discussed last week, it is exactly.
And there is a small arithmetic for the learning rate, right? Inside.
Before you start here, somewhere you specify the optimizer. And when you specify the optimizer, let's say that you choose Adam, which is momentum, Adam W, which is momentum based. Right here, you specify what your LR scheduler is. And by the way, in the solution, I'll show this as an illustration because today I wanted you guys to get a taste of the LR scheduler. Right? So you have the learning rate scheduler. Does that make sense, guys? We'll talk about it. Jay, does that answer your question?
Yes, thanks, Asif. So just trying to recall, the Adam W itself is a LR scheduler.
Adam W is a gradient descent methodology that uses momentum.
Okay, got it. Thanks, Asif.
Nice. So with that, how did we end up with this digression? Where were we before we came to that? Let's scroll up and see. I forgot. Okay. All right. So we'll come to that. I think we were talking about the levels at which you could solve the problem. So you could solve the problem with Pytorch. You could do the training or the fine tuning. It is training, nothing but training a model. You go through the same loop. The only thing is that you don't start with a model that is randomized initialization, but you start with a model whose weights have already been pre-trained, and you do further training. Right. Now, the second API that, and this becomes very low level API. So what has been happening is that people have been asking, can you make it easier than this? Right. Can you make Pytorch a little bit more easy? Now, it's a little bit of a strange request. I mean, if you're very familiar with Pytorch, you would say, like, how much easier do you want it to be? Right. Because Pytorch itself is the code compiles to, or you have something called machine learning compilers. They need to compile it to the actual hardware. Like, for example, it needs to be compiled to GPU. And those ML compilers, or ML, is a deep field. I mean, that's where, for example, CUDA, NVIDIA has a huge leg up. Right? They have figured it out how to compile all of these models, all of these libraries from the Python code that you write, which is very, very high level. It's never going to be executed as Python code, but it is transpiled into the hardware code, hardware instructions for that particular GPU architecture or that CPU architecture. And that's, of course, a very hot area. And if you look at Pytorch, it's a pretty high-level API. It talks in terms of, actually, I think that it talks literally in terms of the textbook ideas. You can map what you understand in textbook to Pytorch pretty intuitively. But there has been an effort to simplify it even further. So there are many, many ways that you could go about it. There are some of these that I will just mention today, which are worth noting. One is people come from the scikit-learn background, and they remember that there you would create a model. Let's say that you created a linear regression model or random forest or whatever it is, or random forest regressor. Pick it is. So I'll just call it model. You would start with an empty model, something like this. And then what would you do? You would say model.fit x train, y train. You would give it the data and the labels. And once it has fit to that, it internally goes to the whole training process. Then all you do is you do model.predict. Either predict for a regression, a y-test, or if you're looking at classification, you would do model.predict proba y-test for classification, CLS. This is for regression. So this is just a very quick recap of scikit-learn, which I trust all of you remember very well. So out will come your y-hat. This is the output from all of these models. Once you get the y-hat, the good thing with scikit-learn is that you have lovely tooling. You can compute, basically, if you look at the scikit sklearn metrics, it will give you everything. So for example, if it is classification, you can do the confusion matrix, accuracy, F1, precision, recall, sensitivity, specificity. Sensitivity is just here, but okay, specificity. By the way, I hope you guys read Sukhpal's wonderful article, why precision should be very particular. They don't ignore specificity. And then you have the ROC curve, area under ROC. And it goes on. And so what happens is that in the scikit world, people have created very, very rich libraries of model diagnostic. At the same time, people have created beautiful libraries to visualize the quality of a model, right? If you remember, for example, one of the excellent libraries is Yellowbrick, right? Yellowbrick library. It gives you beautiful visualization. There are many other libraries and so on and so forth. And now scikit-learn itself is giving you some visualization of model metrics. So you benefit a lot from that. And the one question that people have asked is, why cannot Pytorch look like? Ultimately, it's just a neural network. It's a model. All of this inner training, etc., why can it not all be subsumed in the fit method? And so there is a library called Scotch, which is literally that. It is sklearn wrapper on Pytorch. And today, I'll take that as an illustration to show you a couple of examples using Scotch, right? Because it should put you back into familiar territory. There's another library that does a very good job. It is Pytorch Lightning. Pytorch Lightning not only simplifies or puts a simplification layer over Pytorch and removes the boilerplate code, it actually is, unlike Scotch, which sort of simplifies and purely focuses on the simplification, Pytorch Lightning does a lot more. It actually takes care of some of the harder things, like making sure that if you have GPU, it runs on GPU. If you have many GPUs, it takes advantage of all the GPUs. If you have a distributed cluster, many machines running there, that you have data parallelization and compute parallelization. So these are not easy things to do, right? And in a way, Pytorch is not just simplification. Its main value is that it is really thought long and hard over the Pytorch, the usage of Pytorch, and seen what are the common themes what are the problems that people go through, and then found the canonical solution for all of them. Right? I highly encourage you to use Pytorch Lightning. In fact, you will see what I will do is, last time I showed you code with just Pytorch native. Today, I'll show you code with Scotch. Next time, maybe at some point, I'll show you code samples with Pytorch Lightning. Right? So we'll keep familiarizing ourselves with different libraries. Then the next thing you can do is when you're tuning or training a model, nowadays, especially if you're dealing with transformers, and now, I mean, it is Hugging Face is the Hugging Face transformers. Hugging Face started out as a repository of transformers. You could get transformers. And what they did is that they standardized the API over transformers. And to train, you just need to use the trainer. It again is a simplification layer over even Pytorch, right? You can just get the model, and any model, doesn't matter. If you get it from Pytorch, I mean, if you get it from Hugging Face, it necessarily has to conform to the Hugging Face standard. Are we together? So it becomes as simple as that. You get the model, and model is equal to blah, 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 blah. And you just assume that it will follow the normal things. It will follow, you can assume that the tokenizer is appropriate to it, the model behaves the way it is. So it becomes extremely easy to substitute one model for another. Are we together? And so you can use this trainer API to do that. In fact, that is one of the exercises we have for the afternoon today. We'll use the trainer API. You will go through it. We'll give an hour or two to the trainer API to just learn to fine-tune the model. And I will give today 2 homeworks. And again, guys, you get only 1 week to do it, because next week I will release the solution. For those of you who joined a little bit later, the statement is as follows. We are not getting that much traction on the homework. A basic education rule is release homework when at least people have tried, or at least half the people have tried. We're not reaching that at this moment. So the new way is that we're going to release the solutions fairly quickly. Those of you who are going to try, don't look at it. Okay? Try it, but you get 1 week to try it, because we have a lot of territory to cover in this particular course. So anyway, the Hugging Face transformer is one, and there will be today 2. In fact, the assignments that I'll give you will be 2 projects. One of them is the trees project, and it is sort of a vision related, computer vision related. The other is also related to that, sort of, but it is sound, audio related. It is about barks and chirps, and that is audio related. And I want to, the reason I'm giving 2 different things is I want to make sure that we have complete coverage from text to vision to audio, all of that, right? And this is also very important, because as you know, the big thing that is happening these days currently, and that's extremely hot, is the diffusion models, right? So we need to have enough coverage of the vision areas, computer vision areas, right? And initially, when I started this bootcamp and the syllabus that I had, I was going to do a little bit of diffusion, not so much, but I am, based on how you guys feel, I am thinking that the use of LLMs with video is significant enough. From text video multimodal generation has become significant enough that we probably should do a little bit more coverage, time permitting, but we'll see that. So this is the second level of this. And then the third level is, now there are APIs that are even higher level, right? So let me call them almost like one-liner APIs that make it very simple, just 2-3 lines of code, one to load the data, one to train it, and you're done, to fine tune. And these are one-liner APIs for fine tuning. Like, how much simpler can you make fine tuning? So fine tuning has now been trivialized down to just a couple of liners, and we'll talk about it a little bit. There are quite a few. And then the fourth level of simplification is, forget about even writing code. There are scripts and things like that. So for example, axolotl, etc. they just, and Uber, just they reduce it down to just scripts, feed in the parameters, run it. Then comes even higher level tools like Uber Booga, lovely name, Uber Booga. Right? And this is a tool, this is a lovely tool, and a lot of us were very, very fond of it. And there's some alternatives coming out for this. Which, and so by the way, one-liners, I would, in this category, I would put the XLLM. We'll cover that. And by the way, all of these links are there in your course portal now. If you look at tools like Uber Booga,
you can also add unslot.
Unslot.
Yeah.
Okay, so Praveen here mentions there's something called which category is it in?
Or fine tune.
No code necessary, is it? Just a tool. So I guess it is in the Uber Booga category. Yeah? So this one I don't know, but I'll mention it. Right? I have not played with this. Unslot. So Praveen mentions it's pretty good, and you could just fine tune with Unslot. Right. So as you can see, what is happening is people do fine tune models quite a bit, and because they fine tune, it's become a sort of a universal pastime. And at the end of it, whatever is universal soon becomes commoditized or becomes very, very easy to do. And people have created excellent libraries and tools that make fine tuning a piece of cake. Right. So today we are going to start on this journey and cover quite a few of that. But now, before I go into the solutions, I would like to leave you guys with one question. And think about it. Don't Google it up. Don't start finding solutions, but reason in your mind from first principles. If you have a generative, like a transformer model, remember that the transformer model is a next word predictor, right? And you feed it a question. Let's say you ask it, what's the capital of Paris? It will produce some answer. It has been trained on a lot of data, pre-trained on a lot of data to predict the next word. So these are what are called causal models. And so I'll give you a thought exercise, causal models, because they are based on the decoder part of it, the autoregressive part of it. And so you feed it some input, it produces the next word, next completion token. If I feed it the whole world, web, scrape the web and feed it all knowledge, and it comes up with, if you say, what's the capital of Paris?
Capital of France.
Oh, sorry, capital of France. I apologize. Not capital of Paris. Sorry, capital of France. Capital of France. What is the capital of France? It could give one answer. A. It could say Paris, or it could give another answer by throwing back at you a question. What's the capital of Germany? Right. And the reason it could do that is because quite often questions exist on the web as quizzes, as lists. Right? Students are given, I suppose, in geography classes, they're given this thing. What's the capital of this and what's the capital of that, and so on and so forth. And they're supposed to answer that. So if you train it on a next token prediction model as a single transformer, then it could produce Paris, or it could produce what's the capital of Germany. So that raises a question: how do you predispose it to pick A over B? Right? That is a question, and that is the central question that led to the answering to that central question is actually what led to this whole generative AI movement when it comes to text. Right? But of course, guys, in a way, you may have read the answer or it is common knowledge, but I felt that it is perhaps not so common knowledge. And if you don't know the exact answer to this, don't look it up. Use the lunch break to reason through it from first principles. How would you predispose the machine to produce A rather than B? Is it making sense, guys? The question? Right. That's a question. But leaving that aside, now let's go back to the solutions to the homework. So I suppose I'll just read out the problem. First is, I'll take some of the simpler ones. A model to predict, let's say that, let's take a regression problem. A model to find the sum of 10 numbers as input. So for those of you who did solve the problem, and now that we have greater attendance, how many of you did? I do know 2 people, one remote, Ishila, and one in the class, Prakash Ranade. Anybody else who took a stab at the problem?
I did the first one, the
You did
classification.
the classification. Did anyone do this one? Find the sum of 10 numbers. Anyone at all? Ishila, did you? Oh yeah, Sanjay, you did it.
I did. It's not 10 though. It's like variable.
Variable
The
numbers.
length of the numbers in a list is variable.
But what's your maximum number size?
Because I treated like a large data set. 10,
Okay. So you took a variable number. And how many layers did you put in your network? 4 layers. How many nodes per layer?
24, 24.
24, 24, 12. Okay, that's a good answer. And you got a pretty high accurate, what was your net MSE loss at the end of it?
Was pretty bad.
It's pretty bad. Huh? It didn't converge.
It didn't.
In fact, many of you saw that the thing would blow up.
Yeah.
The
Some wasn't close at all. The negative was little close.
Yeah, the sum of the inputs was not close at all. So can this problem at all be solved using a neural network? How about you, Prakash? Did you do this part?
No.
You didn't do this at all. Okay. Anybody who did that?
Close.
Okay, some were close, some were far. Okay, good.
I tested I tested
Yashila, go ahead.
I tested up to 5 hidden layers, but to be fair, like how the layers work is essentially to just add everything together, right? So input layer, output layer. For the
That's right. So how many layers did you have in your network, Yashila?
my final answer was essentially to put an input layer and an output layer and then train for the weights in between, because every other set of layers didn't really work. Like I tried up to 5 with up to 1,000 nodes in each of the hidden layers. I tried as a standard, like for each of the layers, like 250 and then 500 and then 1,000.
And what did you realize at the end of it? That your network...
Yeah, the added complexity doesn't make this problem more solvable. Input layer, output layer, just add everything together.
Yes, in fact, I'm so happy that somebody could answer this question. This is really hats off. So now what if I told you, guys, that this problem, and in a way, you pretty much hit upon it. Let's think about what a neuron is. And this is what I say, thinking from first principles. What's a neuron? What is a neural network ultimately? It does a linear transformation followed by a deformation. Is that correct, guys? Each neuron takes the input, does a linear combination of it, and then does a deformation. Is that true? So this is what a neuron is. It is made up of 2 parts. Z is equal to W dot X, Wi, Xi plus B, right? It's summation of the W's. Is this correct? X1, X2. Suppose in this case, it is X10. So what is, and then this B, the bias is coming in from here. Are we together? And this does the sigmoid of this to produce your output. Are we clear, guys, on the neural network? This is it. This is one neuron. We are looking at it under the microscope.
So it does a submission on X1 to Xn?
Of course. That is what literally a neuron does, isn't it? So this is the linear part, linear transform, and this is the deformation. Or I call it deformation. The more technical term is non-linear activation. It does a non-linear activation of that input. Are we together? Now, look at this problem. When you write it like this, guys, I'll ask you, suppose the weights are 1, 1, 1, 1, and the bias is 0. What is Z? What is Z?
Sum of all.
Xi. Is that not what you were going out to compute?
Yes.
And so what does your neural network really need? Pytorch neural network needs what? Just the input layer, right? With one neuron.
It's a higher.
And no activation.
Weight.
No activation. Z is the identity function. No activation at all. Do you see that, guys? Right? And you can randomize the weights and the biases, but this machine, as it goes through epoch after epoch or runs through the data, exactly what will it learn? It will learn that there's a bias is useless and weight should be 1. Does that make sense, guys? So you realize that actually adding more to it is counterproductive. Creating large layers and so on and so forth will actually be counterproductive. And we'll see this. Now,
Counterproductive for this arithmetic problem, right?
with this arithmetic problem, yes.
Not
So we are just going to look at this problem. So summation of the inputs. So this is here. Oh, by the way, just for fun, I took Scotch. Remember, I said that I'll make it look like scikit-learn, because last time we did Pytorch native. Here, I've wrapped up the Pytorch in Scotch, which is a scikit-learn adaptation or wrapper around that. And next time, maybe I'll give a Pytorch liking example. So here we go. We have, so first of all, you need a data generator. Let's go over the data generator. Actually, this project was more about just creating simple data sets than anything else. So here is a data generator. Generate summation data. What do? You go and generate. First of all, you have a helper method, generate inputs. What does it do? You give it boundaries, let's say 1,000 minus 1,000. And within that, it will go and generate lots of points and shape it into a matrix so that you can generate your data. Right? Once you have generated the data of a certain shape, X number of rows, X number of columns, when you do summation, what do you need to do? You need to produce the label, isn't it? Input is the input you generated as an X matrix. Now you need to produce the labels. Y is the labels. Label is what? It is the sum along the rows, isn't it? That's what we are doing. We're making it as a sum along the rows. Very easy. Likewise, if you want to find the max of n data points, how will you do? Almost the same. Everywhere is just what is their label to be. Your label in this particular case is whatever is the maximum along the row. Standard deviation is standard deviation along the row. And then negative data, what do? You create negative data in two parts. You first create two matrices, like half a matrix filled with negative and positive, potentially negative and positive data. And this, then the other part in which, if you find a negative, flip it so that you get about 50% of the data which may have negative numbers, and another 50% of the data where you took precaution and made sure that you flipped every negative to positive. Make sense, guys? Okay. So this is just data. So guys, I hope there's no mystery. If you have a question, this is a great time to ask me. Any mysteries in the data generation? Is data generation looking obvious and easy?
Why can't we fit just a list of numbers? Why are we creating a data?
Because each input is an array, right? Each input is an array, and so the whole data set is a matrix. Right? That's it.
No wonder why ChatGPT gave me like 20 neuron solution.
Okay. So why did ChatGPT give you 20 neuron solution? This is actually a good question. Can somebody answer why would ChatGPT for such a simple problem produce a 20 neuron solution?
20. Just to be on safer side.
There
Just
is
to
no
be on-
reason. There is no reasoning behind the solution, but it's a good brain teaser.
Yeah, the main reason for this is, see, it again comes to the next token prediction engine. It does local optimization. It's a greedy algorithm, right? At the end of it, it has rarely seen people solve problems with 1 neurons. Who in his right mind would do it? After all, everybody is sitting on 4090. What a criminal waste of 4090 to create a 1 neuron solution, isn't it? Right? So well, obviously, what is the most common sizes of neural network these days? Well, 20 or something close to that. And so it is trained on that data. It has seen code like that. So therefore, as a next word prediction engine, it has come out with that solution. It is not a reasoning engine. At least we have some indication that these LLMs are beginning to reason. These are emergent abilities in large models. And again, it is a highly debated topic. If you ask Jeffrey Hinton, he would say, yes, LLMs are beginning to understand and reason. Flawed reasoning, but they do reason. If you ask Jan LeCun, he says, no, they're just stochastic parrots. So the jury is out at this moment. We don't know. But the fact of the matter is, the fact that it produced a 20 neuron solution inclines you to think there is something of the stochastic parrot in there. Right? Why it's not capable of ab initio thinking. Prakash.
Yeah, so in my exercise, I did a torch tensor and gave an input of
that is perfectly fine.
But
you can do.
Why we are doing this standard deviation and all this thing in the generation of the data?
Look at this. There is a problem here. Regression, a model to find the standard deviation of the inputs.
Oh, okay.
Right. So I'm creating the data set for all of these problems.
I see.
Okay.
We can create data by tensors.
Yeah. So one question that some of you did is, can we not just use the tensor API? And the simple answer to that is, of course, you can use it. Here, what I tried to do is, because the whole point is that these are baby steps with Pytorch.
Right.
So I used the least amount of Pytorch and kept you in the familiar NumPy and scikit-learn territory.
Okay.
But here is the beautiful thing. And this is what made Pytorch really make people love Pytorch. Pytorch has put in a lot of effort to be literally function API compatible with NumPy. So everywhere that you see the word NumPy here, NP here, just replace it with the word torch. It will still work. Do you see the beauty of it? Not only will it work, it will be simpler, because if you notice here, I had to cast it explicitly into float 32. The reason is NumPy by definition works with 64-bit floats, whereas there is no such space, hardware space available on GPUs. That is one practical reason. And the other reason is the weights and biases of the data that most machine learning deals with are normalized data. There are fluctuations or perturbations around zero. Right. So you could replace everywhere that you see NumPy with just the word torch, and it would still work.
And everything done on GPU.
And everything we'll do it on the GPU. So all right, guys, and so this is that. Let's go and look into our network. Our first network should be the summation network. So notice that what is our neural network? What do we do? Our neural network is made up of just a linear layer with how many inputs? 10. And what is the output dimension? 1. Isn't it, guys? It's basically this picture. This picture, 1 neuron, is 10. Remember, output dimension tells how many neurons are in the layer. When your output dimension is 1, means in that layer, how many neurons are there? 1. Right? So 10 inputs going into 1 neuron producing an output. That's what we are doing here. And let's look at so any questions, guys? What is the forward? All you do is take it and feed it to the output, isn't it? Does that make sense, guys? Right. And then let's see how well, by the way, the same solution I've given it to you as a Python script, as well as, like, for example, you can go and run it from the Python script here, or you could go and run it from the Yes, and is this the solution is all here, guys? Huh? It's all. Where is the solution, by the way? Solution is Pytorch website. So this is the homework, and if you go to the course somewhere here, you'll see that. So all the solutions are here. You just have to look at the topics. Oh yeah, here you go, day 5, right? Day 5. Here are the solutions. So you can download the solutions if you want, but wait till the lunch until you try it out. So let's look at the okay, the code. Now I'm going to go and this is it. I'm going to create the summation of numbers. This is the neural network. Now, how many epochs? 40, maybe. Now here I'm not using a learning rate scheduler. I'm just choosing a fixed number. People have their fixed number. I tend to be very conservative. If I don't know anything about a problem, I'll always start with 10 to the minus 5. Very small learning rate. Right? You can start with 10 to the minus 5, 10 to the minus 3, whatever it is. A batch size 16. These are very typical numbers. So I would suggest that if you don't know anything about the problem, start with these sorts of defaults. Right? What is the loss? What is this MSE loss? Can somebody enlighten me? What is that MSE loss?
Mean square error.
Mean squared error.
Excellent. A mean squared. And why are we using mean squared error? Because it's a regression problem.
Regressor.
Excellent. And a device is obviously, if you have the GPU, then go with GPU. So what we do is we produce the data. We produce 2 batches of data. One to produce 100,000 data points for training, 100,000 data points for testing. So it's sort of a 50-50 split. And then we have the model fitter. Let's go and see what in the world does our fitting loop does. Well, it turns out that if you use scikit-learn, you don't have to write the double for loop. You can fit. Let's go through this. And as you notice that I'm using the Scorch library. When you use the fitter, regression, here you do the fit, evaluate, and plot. All 3 it will do. And it becomes pretty straightforward. So let's say that you go into fit prediction. What you do is model.fit. Does it look exactly like scikit-learn, guys? This is scikit. You wouldn't know there's a neural network. Scikit-learn, you get the prediction, you return the prediction, right? Plot loss, and these are things that I trust you can review and read it on your own. There are no mysteries here. Classification, fit again, predict. What is the metric you would use for how would you know that your model is good? You would look at the confusion matrix, amongst other things. Regression, fit, evaluate, and then plot the loss. Right. Now, here's the thing. If you're using a regression problem, one easy way that you could get a sense of how good your solution is by just quick and dirty ways to look at the, even if your loss has flattened out, sanity check. Just see the correlation between prediction and reality. Y and Y hat, right? Basic correlation. So that's what I'm doing here.
Hand up if you want to take a question.
Okay, go ahead.
Oh, so this is for one of the other questions, but for the max, like finding the max of like the data set that you feed in, I ended up using an L1 loss instead because that kind of like biases you towards extrema. Was that the approach that you'd intended to use, or did you also use an L2 loss?
And so no, let's say that you use a L1 loss. What did your network look like? How many layers did you have in your network?
My network had 3 hidden layers.
3 hidden layers. Now see, L1 loss is good because in this problem, this sort of problem, because when you do it with that, your y minus y hat squared can quickly lead to infinities, right? Out of bounds. And I assume that you began to notice that and you use the L1 loss.
Mm-hmm. That's basically
so, that's basically it. And that is the correct thing to do, right? Though wait for a bit of a surprise.
Okay, good to know. I know that we went over this in one of my classes before, but I'm just completely basing this off of the intuition that I've retained.
So,
But I'll come to your problem. Yeah. There's a bit of surprise waiting for you there. Yeah, go ahead. Somebody is saying something.
so as of for some of the numbers, there's no back propagation there, right? It's just a
Oh,
forward.
backpropagation always takes place, always. Because see, think about the simple neuron itself. When you randomize the weights, here, one neuron network, how will the machine discover that the weight should be 1 and the bias should be 0? You can see it, obviously. But how will the
Okay,
machine? You need to backpropagate it. Right? And
got it.
so we do that. And so let's do that. When you do that, fit evaluate, look at this. You see that you start with a massive training loss. In fact, it's dangerously close to blowing up, right? Which speaks to the value that, for example, Ishila brought up that could we use a L1 regularization on the MSE loss. Okay, so here we go. At the end of it, though, what happens by the time you reach the 40th? What have your losses become? Zero, right? Now, I bet you, if you use a multi-layer network, you had a slightly harder time getting to zero, isn't it? So the lesson there is, guys, that if you think from first principles, you can often solve the problem easily, and B, you can get a much better solution than if you blindly throw models at it. And look at the correlation between reality and prediction, 100% correlation, right? And look at the loss. You want to see loss diminish like this, isn't it? This is the loss flattening out, and it flattens out at 0, right? So I suppose that's compelling reason to believe that it has found the right answer. Now, what are the parameters of this model? Let's look at this. Is it something that we would have expected? Look at the weights. What are the weights on all the 10 inputs? 1, right? So machine has found the art of adding numbers. And what's the bias? 0. Isn't it, guys?
I'm thinking about the intention behind, framing such a homework.
I was just going to say, you just cracked AGI.
So, yeah, Sipal, you have a question?
No, I was saying, did it learn or just
No, it learned. It learns. So now I'll ask you this question. Suppose, let's go through the simpler ones. The next one is to detect if the sum is greater than 100. Right? Guys, think about it. Think from first principles. This one looks hard, right? You have to find the sum, then determine whether it's greater than 100. How many layers do you think this one needs? Let's go back and think from first principles. See, can you determine, suppose if I have a neuron B and my bias is equal to -100, right? Suppose a machine has a bias of -100. Now think about it this way. All the weights x1 to x10 come through and you do a summation. Suppose all the weights are 1. What will your z be? Xi -100, right? And let's say that you have a ReLU function, you attach a ReLU, right? Or you attach Gardner's. You can attach a sigmoid. Let's just say a sigmoid Z, sigmoid. Doesn't matter. Now the sigmoid Z you attach, what will it do? What does a sigmoid look like? And this is where I wanted you to think about activation function. What's the nature of a sigmoid? This is the probability axis. This is the probability of something, and this is the value Z, right? Z axis. This is what? It asymptotes at 1, and at the negative, for all negative data, it asymptotes at 0. And what is this point at the x-axis, at the y-axis? What is this value here? 0.5, isn't it? So what does it mean? do you realize that I can just take one neuron, but this time add an activation function to it? It's a classification problem. I need to make it into a classifier, right? So I need to bring in that activation function. Is that easy? Right? And therefore, let's go and see if that's a solution we came up with. So again, guys, what I'm trying to reiterate is, if you want to have fun with this subject, try to think slowly, carefully, not rush ahead. And I'm reminded of the book, the marvelous book, for which the author got the Nobel Prize. For that research, he got the Nobel Prize, Thinking Fast and Slow. Has anyone read that book here? So our minds have two engines. One is intuitive, life-saving, on-the-spot decision-making to protect you. Most of the time it is right, but for many intellectual tasks, it actually takes you to the wrong answer. Right? And then there is a slower part of your brain that evaluates, that reasons. That's not the part of the brain that you use when you see a tiger. Right? You run away from it. You use the fast part of your brain. But it is the one that often helps you create elegant solutions. So now here I introduce a learning rate scheduler. Why? Because just for fun, just to show that you could. So I will, and here it is the step learning rate. Okay. Now, what is the loss for a classifier? For a binary classifier, is it greater than 100 or less than 100? That is a binary problem. What's a good binary classifier loss? Cross entropy loss, binary cross entropy loss. So I use the BCE loss. Right, here it is, BCE loss. The rest of the code looks exactly the same. Let's fit it and see what the training loss and validation accuracy is. You notice that the training loss drops precipitously by the time you go to even fourth epoch. And accuracy is already hitting 99.13. In fact, going through all of these rounds is negligible, but because you are dealing with a classifier problem, and these are small numbers that you're dealing with, you notice that you have a confusion matrix that is like very high precision recall. In 200,000 rows, it got 138 off. Okay. So look at the loss function, how it propagates. You notice that it flattens out pretty quickly.
Fantastic.
Now, let's look at the negative number detector. Oh, that must be tough. How do you detect negative numbers? Can we do it with one neuron? By now, everything seems possible with one neuron, right? So, how do we detect negative numbers? Anybody wants to venture a guess whether this is possible with a neuron? Which way would you bet if you had to bet? Anybody? Hey, you have nothing to lose. You can bet anyway. How would you bet? Okay, let's reason through it again from first principles. See, guys, this is where, I feel that knowing the foundation, let's think about the activation functions. Right? What does ReLU look like? Rectified.
Anything negative is 0, right? So
That is right. When Z is negative, it's 0. When Z is positive, it is whatever the value is. So basically, a ReLU is nothing but a diode. That's why a diode is also called a rectifier, right? A rectifier. Current can flow in only one direction. That's what a ReLU activation is. Does it make sense, guys? Right. So now tell me, if I gave it an array of some positive and negative numbers, and I passed it all, each of the numbers, let us say, went through the ReLU individually, what will you get? You will get an array in which what will happen to -3, let's say 4, 7, -9, 11. I'm just taking an example.
Zero.
What will get 0? All the negatives will get 0. So therefore, if my problem was to detect if there is a positive number there,
Anything greater than zero.
right, what would I do? I would just feed this into a single neuron, right? And again, once again, the sigmoid that we created, you realize that if I feed this into your summation, right? The Z is equal to the summation of Wi xi plus b, assuming all the weights are 1, for example, what will I get? I'll get a positive number, right? And if I pass it just like we did, I pass it through a sigmoid, my probability will be greater than half. Isn't it, guys? It will be greater than half because the sum of the positive numbers is positive. Positive numbers produce a sigmoid value greater than half. So it is a perfectly good, a rectified linear unit. So what I could do is I could take a rectified ReLU, pass the input here, pass it to a neuron. This is your Z, and this is your, once we have that, all of these are going in. And this would be a perfectly good classifier that detects positive numbers. Does that make sense, guys? But your task is to detect negative numbers. So how do you detect a negative number?
Zero.
You say that all you need to do is, if this is x, x prime is equal to -x. So suppose I take -x, it becomes 3. All positive numbers become 7 minus whatever it is. Let's say that -9, -11. So now what happens? When I pass it through ReLU, what will it do? It will go and cancel all the positive numbers, because I flipped the positive numbers to negative and negative to positive. Are you seeing that, guys? And so once I pass it through, so all I need to do is create a network, a layered network, in which I have to first do ReLU -x and then feed it to exactly the same network that I just now created.
And if you get zero, then it's a positive number. Is that what you're saying? Output is 0.
Yeah, if the net output is 0, then then you basically say that it's a positive. There are no negative numbers, because if there were negative numbers, you wouldn't have gotten 0. So is it making sense, guys?
So Asif, while you gave the homework, you said not to play with the equations, right? Like, don't. In here, you put ReLU -x. That's a little bit of cheating.
Perfectly okay. That you do all the time. You take the input, you flip it upside down.
Okay.
See, given the input, it is very common to flip, to normalize, because suppose your input is made up of large numbers, right? One of the standard normalize, scale the numbers. These operations are like, okay.
Yeah, Asif, I have the same question as Jay. Our objective is to have machine learn, right? So without having to pre-modify things.
You're not pre-modifying. See, one conscious decision you always make looking at the data is what is the topology of my network? And then you learn the network learn, right? You're just thinking through the topology of your network. Albert.
Why do you need to make it to -x, right? You can just say ReLU, and outside, if you get anything
no, it
positive,
won't, because it will suppress all the negative numbers and there will be nothing left to detect.
Oh, okay. Now I got it.
So anyway, guys, this is an exercise in which I just wanted you to realize the simple thing that sometimes thinking through, and this is this is a very, very, very trivialized example of something that is called neural architecture search. Thinking through the proper neural architecture, and there's a whole field of learning called automated machine learning, of which neural architectures are. So they are machine learning algorithms whose job is to produce the best neural network that will solve the problem. So given a data set, given a problem, they don't actually solve the problem. They instead reason through and find the best neural network that should be used to solve the problem. Right? So the first machine learning task is to give birth to a neural network that will, as a child network, go and solve the problem. So that's a big topic. We won't go there. But as you can see, this leads to this thing. But what about standard deviation? Can you solve standard deviation with this? Let's reason through standard deviation. Oh, by the way, I didn't put it in the solution, but that is very easy. Guys, I'll take questions in a moment. What about the one that is the easy one? Find the max of the numbers. It turns out that to find the max of the numbers, you don't need anything. Tell me, what does the softmax do? Softmax activation does what?
It does an exponential and get high value.
Yeah, but what does it return you?
Probability distribution.
Yeah, so what it does is that if you give it some numbers, -3, 2, 1, 5, 9, 0, it will convert it into a histogram and it will find you the tallest so it will do e to the x over xi summation over xi. This would be the probability of xi. So what will it do? Which number will have the highest probability?
The largest number.
The largest number, right? So what do you need in your network? You don't even need anything at all. You just need a softmax.
We can also use ReLU, right?
You can use ReLU to do what?
The largest number will have the
biggest. Yeah, you could do ReLU and then pass it to softmax to find the biggest. But my question, my thing to you is, as a classification problem, why bother? Right? So guys, these problems, when I crafted, I literally cooked up the problem. If you remember, I was standing there and out of the top of my head, I just cooked up the problem. So I picked up things that would make you think, basically, right? And that admitted very simple solutions. But it's good that you played around with Pytorch and did that. But the lesson to learn is, guys, don't forget your fundamentals, right? Sometimes the answer is far easier than you think. So this is finding the biggest number, right? Literally, that is why softmax exists. And if you remember, I'd asked you guys to know your activation functions well. Yeah. It is as simple as saying, that's what softmax does. We are done. Right? Now, then comes the standard deviation. Go ahead.
Just one question. So you said the auto ML thing, will that be able to figure out this network, Asif? Or
it will.
Oh, okay.
Bayesian optimization process will discover it in no time.
Okay, thank you.
Yeah. So obviously, you can either reason through it or have a network discover the network to solve the problem. It's fun, by the way, auto ML or this whole field of Bayesian optimization. Many of you know that it is considered so seriously that a consortium or a group of people have invested close to $1 billion to just this subfield of neural networks to help it grow. This is what I'm told. Okay?
Yeah, so just for correctness, I wouldn't be missing a E in the sigma for the softmax.
Come again, what am I missing?
E in the sigma EXI.
Oh, sorry. Yes, you're right. Again, I am always very sloppy. Thank you for pointing that out. Yes, a summation over I. So that is one. And while we are being exact, let me actually tell you, this is the way the softmax is given in books, but actually strictly when you implement it, don't implement it like this. Implement it always by what people do, of course, is they do X max. For numerical stability, they put X max here. They look at Xi minus X max so that all the numbers are to different degrees small. The values are all small because exponential can blow up, right? You can easily have infinities So, well, that's sort of a computation, but for now, let's not pay attention to them. Just not look at that. But the classic formula as in textbooks is just e to the xi over summation of xi's. All right, guys, so that is that. Now we'll come to the one, it seems that the world is, all problems in the world can be solved with one neuron and hardly any activation function at all, or maybe just a simple one. Let's see if we can do better. What happens when you go to, and as you notice that if we go and try to do a standard deviation, can it be solved with one neuron? Think about it, guys. And again, think from first principles. What is standard deviation? Is the summation over xi minus x bar, the mean, right? It is the deviation from the mean squared and summed over it. I mean, the square of standard deviation is variance. Let me write it out if you, in case it has eluded you. You have variance is equal to summation over I xi minus mu square. Does this make sense, guys? If you expand it out, it will have xi terms, it will have mu terms, xi terms, and it will have xi square terms, right? The zeroth order, first order, and second order terms in xi, right? So this, to compute this variance, and of course there is a normalization terms, variance terms. It will have all three zeroth, first, and second order terms. So can you get a second order term from a single term? How do you get that? Anyone? Remember your basic rule of algebra that I keep quoting, that every time you bend a line, what do? What happens when you bend a line?
Slope changes.
Slope changes. Specifically, you introduce at least one higher degree polynomial, right? So think of this. This is a straight line. Right? I bend it. What is the smallest polynomial that can describe it?
Square.
Square. This is a quadratic equation, right? It becomes quadratic. If I bend it again, what's the minimum degree polynomial that can approximate it?
3.
3, exactly. This is one of those things they taught in school, but never with the significance of what it means, unfortunately. This is the fundamental theorem of algebra, right? So imagine that we have all gone through years of algebra textbooks, and somehow we missed that. And the reason for that is very simple. It will have 3 zeros, 3 roots, right? You need to create a solution with third degree polynomial, 3 roots. You need to at least bend it twice. Yeah. So this is it. So now think about it. If I take a linear thing and I want to produce from this x as an input, I want to produce something that takes at least x squared. What do I need to do? I need to bend it, right? Does it make sense? I need to deform this line. What deforms a line in the world of neural networks? What deforms a line? An activation function. So I need an activation function. And now you realize why activation functions are at the core of achieving the universal approximator behavior, right? So pick any approximator function. So for example, if you take a sigmoid of x, what is it? 1 plus e to the minus x, right? If you do the Taylor series expansion of this, you'll realize that it contains, oh my goodness, it contains unit terms, zeroth x squared terms. There'll be an x order term. There will be a term, x squared term will actually not be there. There'll be x cubed terms. So does that look bad? We can't use sigmoid. What do you say? No, you can, because what happens is if you take the square of anything, so for example, you take the xi minus mu cube cube. Let's say that there's a cubic term there. What will the expansion contain? It will contain 0th order, x term, x squared terms, x cubed terms. So your x squared terms will anyway be there. Does that make sense? Right. And so all we need to do is make sure that we create a neural network that has deformations built into it. Not only deformations built into it, you realize that there is summations going on, right? First, there is you need a deformation of each of the inputs, right? That you can do with the activation. Then there is a summation going on. The summation can only happen in the next layer, right? So it looks advantageous, even though you can do it in a single layer, it looks advantageous to use, or more efficient to use at least 2 layers to create this neural network, right? To make it a multi-layer perceptron for that reason, right? And that is what I did. Standard deviation, you make it into a multi-layer perceptron. Where is that code? Calculator. Simple negative binary. Oh, by the way, now I don't know if I went through the code. Now you would agree that simple binary classifier to tell whether it's greater than or less than 100 is very easy. You take the input, pass it through a sigmoid. That's it. Negative binary classifier, just use a trick. Before you pass it through the simple process, just minus it. Okay. And so on and so forth. And so, but I'll give you an interesting problem after that, which is a little bit harder. Yeah, this is your multi-layer perceptron. So here, just for fun, I chose a larger layer to emphasize that even though the universal approximator says that a single layer of neurons can approximate any function, if you try to do standard deviation with just 1 layer and 10 or 15 neurons, you'll struggle. You will struggle to converge. Whereas if you try it out with multiple layers, it will converge very, very fast. And I invite you to do that experiment to gain intuition into how these things work. You will notice that this converges very fast. It won't converge so well or fast if you do and you notice that the correlation between numbers and their predictions are 99.92% or 93%, right? Very high. So I threw in something that I had not initially mentioned, but later on I added to the portal. These machines, these neural networks, what is the limit that we can push them to? For example, can we find the factorial of a number? So factorial of a number is what? What is factorial of 5? Nice. You take all numbers from 1 to 5 and multiply them with each other. 1, 2, 3, 4, 5 multiply. Right? That's 5 factorial. Right? But the problem with factorial is it blows up very fast. Isn't it? So if you were to train a neural network, so the first question is there a function that describes a factorial? Surely there is, isn't it? Literally that function that we talked about. But can we approximate it with a neural network? It should definitely be possible. But there is a practical problem. What's a practical problem? To train a neural network, you need sufficient data, isn't it? Training data. But, by the time you reach n is equal to 20 or n is equal to 30, you realize that your output is huge, isn't it? Those factorials are massive. So you cannot go and create 1 million data points, right? Or a large number of data, 100,000 or 10,000, or even 1,000 data points, right? Try doing factorial of 1,000, you'll see what it does, right? You can't. So you have a real practical problem. How do you train this network? So who would like to take a stab at this? How do you train this network? You can, right? Come again?
Divided by a very big number.
You keep thinking it doesn't help you. Go ahead.
I think it has to do with figuring out. The network has to figure out what numbers it needs to multiply, rather than arriving at the answer itself.
No, that is all right. It will figure it out that it needs to multiply the numbers, the inputs. But for the neural network to get there, it needs enough data to be trained to figure it out. The trouble with this is not the neural network part, but it is the data problem. Where do I get all the data to train it with? Remember, you're dealing with float 32. Float 32 has a limitation. Okay. Yeah, very soon you'll start having infinities. So, well, this was a slightly hard problem, but I wanted to show that sometimes getting a little bit deeper does help you. So it turns out that you have in your past encountered a function in your engineering math textbooks. Does anybody remember the gamma function? Or heard of the gamma function?
Yeah.
So gamma function is literally a generalization of factorial to floating points, to decimals, right? So you can find the gamma of any number you want, but if it happens to be an integer, it becomes a factorial, right? So gamma of 11 is 10 factorial, right? One less than that. The moment it becomes an integer, it becomes a factorial. So it's a generalization of it. So what can you do? This is the lovely integral, and I keep singing praises of transcendental functions, that they rule the world, and here is one. This gamma function has this property that gamma of n, where n is an integer, is n minus 1 factorial. So therefore, now is my problem of data creation solved? Can I still now, in a very small interval, let's say 0 to 5 or 0 to 10, create gazillions of data points? Of course I can, isn't it? So I can. And so we do that. I wrote the generator for the data right here itself. Oh, I think it's complaining. Oh, maybe I forgot to import it or whatever. No, I did import it. So here's the gamma function. What you do is I took an interval which is very short, just 1 to 22. You can make it even smaller, 1 to 10, or whatever it is. And you compute the gamma of that, and you use that as an input. And then you train your network. You can train your network. You can, just for fun, here's the factorial of 10, it is this, or factorial of 5. And actually, I took, in this particular example, I took a range of just 0 to 5, just to show that you can solve it. Now, you may say 0 to 5 is too trivial, but just to illustrate the point. And so what happens is that this network does converge for a range of 0 to 5. Now, when you go to 0 to 10, it will work, but you'll have to be a little bit smarter. You can't take a uniform distribution of training data. You'll have to have a lot more data at the beginning of the range. Like 0 to 5, you need far more data than you have for the much larger range. It will converge. I leave that as an exercise for you. The trouble is, it doesn't, like, it gets unwieldy after a little time, right? Simply because of the limitations. Finally, we come to the prime number detector. What about prime number? It turns out that there are 78,498 primes below a million. I said, write a detector for prime numbers below a million. Right? Now, I don't know if anybody in this batch, Yashila, did you try that?
I did it a slightly different way. I set my limit to be 100, like an upper bound of 100 and then nothing below 0 for the training data. But I also have previously implemented like the sieve of Eratosthenes, like when you generate the training data itself, which is essentially every time you find a prime, check it against the existing known primes, or try to see if like the largest, like the square, like the closest prime to the square root of this number is a like factor.
No, I'm familiar with that algorithm.
Yeah.
So you didn't do it with the neural net, or did you do it with neural net?
No. I did it with the neural net, and I just gave it like the list of, or I basically just like created the training data and then just gave it like 5 layers or whatever, and then it worked fine. Like it actually worked really well, but I didn't try to do it in a smart way, I guess.
What was the accuracy you got? Prediction accuracy?
Let me check. I also didn't I did this based off of what we had talked about in class, and I actually predicted the number of primes like in the data set as opposed to the
okay.
Yeah.
The
So my
is
final
okay.
accuracy there, my like MSC loss was 1.9, which I thought was pretty good given the fact that like the data sets that I was throwing in were like 100.
Yes. small data set. See, it works very well for up to 100 and works even up to 1,000. By the time you get to 1,000,000, you begin to get into trouble. You may notice that it begins to saturate in the 80s. The accuracy begins to saturate in the 80s. But can you reason through why? So see, neural networks are universal approximators of functions. Is there a known function that mathematicians know? Can they say definitively that there exists a function that generates primes?
No.
No, we don't know the definitive. Nobody has found the function, and we do not know definitively whether such a function even exists. But it's certainly quite elusive, isn't it? So that's where you hit upon the limitations of neural networks. Right? At the end of the day, they are universal approximators. The approximators of what? At least there has to be a presumption of a function. Right? And so if you look at it, there are 78,498 primes below 1,000,000. That is about 7.8% probability, right, for something to be a prime. And so if you take a set of 10 numbers, what is the probability that none of them are prime? It's about 44%. It's combinatorics, and therefore the probability that there's at least one number that's prime is the converse of that, about 56%. So any classifier that you write, it needs to beat this, do better than this, doesn't it? Right? So that is your baseline. But the reason I threw this problem is you will never be able to, for a sufficiently wide range of numbers, ever be able to create a neural network that genuinely, with near 100% accuracy, detects primes, because it is quite possible that such a function does not exist. Right? So that gets into, and the point of bringing this one is to, again, to reiterate that there are things neural networks can do, there are things that it can do very easily if you think about it, and there are things that it cannot do. So with that, I would like to take what's the time now?
Quick follow-up question to that, though. Wouldn't the neural network be able to, in theory, encode like a sieve of Eratosthenes type of approach, like if it were like a recurrent neural network? Because then it doesn't have to actually remember what a prime is. It just has to basically see, have I seen a prime before? Does it match the list of primes that I've previously seen? Right? Like a simple attention network should be able to do the same thing because it has seen primes before and it has identified them as primes.
Yes, actually, you raise a very good point. Now, here's what I'll tell you, and you hit upon what I was going to say. See, because a network can contain primes that it recognizes if you have trained it it is a sufficiently big network, because networks have parametric memory. If you train a sufficiently large network with attention, what will happen is the attention network will immediately, the weights will remind it that these are primes. Right? Or it will remember the primes. And so, given an input, because somewhere it remembers the primes, it will start paying attention to those primes that may potentially factorize a number. And by not finding any of the primes in its parametric memory that could potentially factorize that number, essentially, it is coming very close to implementing the sieve algorithm. Does that answer you?
Yeah, I think it's interesting because it has other implications around like what does like what would an LLM do if it encountered like a prompt that it's never actually that it doesn't have any training data for, right? Because like in some ways it's basically like saying I have one side of this algorithm, which is like the cached part of the algorithm, which says I've seen previous data that matches what this prompt says, and therefore I'm just going to exploit that. But what happens if I haven't seen it? Well, can I just kind of break it down into something that I have seen before? And if not, then we run into problems, right? Like then we would have to encode it as like a new set of data.
Yeah, I mean, this is an experiment that I suppose can be easily verified. Let's try that. Let's try that. Let's go to ChatGPT or something, right? Or chat. We can go to that, or there are comparators also, L MS, this one. Let's try this one because it will try multiple of these chatbots. So there are two chatbots. Let's give it the same input to both of them. We'll say, so it has probably not seen this input before. Pi it has seen. So let's just make it.
Okay.
So there you go.
But well, extending her question. So suppose if I train the neural or transformer for, let's say, prime numbers up to 10 million. But I mean, that's just not parametric knowledge. Right?
Yeah, it's parametric.
Obviously, it cannot predict anything beyond that.
That is right. So see, Krishnan, the point that you make is very good. You can take sufficiently large networks, throw in attention, do everything and train it. At the end of it, it has to be, is it parametric knowledge or not? It is not just a academic question. It has become a legal question these days. With the New York Times suing these LLM makers saying that, hey, your copyright infringement, it can regurgitate our text. Right. So initial belief was that weights and biases don't store information. Now we know they do. Biometric memory is very real. And so how often is it responding from memory and how often it is actually bright enough to solve it? That reminds me of a course in undergraduate. So it was a tough course. I used to love it very much. It was one of the harder courses in electromagnetic theory, antenna and propagation. So most people found it tough. And I love that subject because it's physics and so forth. I prepared really hard for it. I went to the exam and then I came out and got really bugged because I didn't get the highest. Right? So who got the highest? Here's this guy who had no interest in the subject at all. Like as far as that subject was concerned, a total barbarian. So we were like, what? How did you get there? No, he said it's very simple. All I did is I knew the previous year's questions. I made a database of 20 questions and he showed me his notebook. Perfectly written answers, the best possible answers that you can't in a time constraint ever think of doing. Every single nuance thought out. He says, these 20 questions, I just memorized these answers. And who answered these questions for you? Oh, I just went to different people and took all their answers and put it together, compiled it. Right? And he said that, see, look at it. This exam paper was straight out of those 20 questions. Right? So he turned out to be the brightest guy in the class. Right? And so a very similar situation is true with the LLMs today. But to what extent do they understand? To what extent are they reasoning? To what extent are they regurgitating? And therefore the debate between the great luminaries like Hinton and Goodfellow and Jan LeCun and all of these people. One extreme, people think it's a stochastic parrot. Another extreme, they say, no, it understands and so on and so forth. So who knows?
More questions, So how complex LLM, all the differential equations, integration, stuff like that. Can LLM solve those problems?
Differential equations, etc. There's a whole body of research that's trying to apply a transformer architecture to solve differential equations. And in fact, with success with fluid dynamics and other things, we are getting pretty good results with neural networks.
So, but the concept is essentially it can break down into sub-problems.
Yes, it can do that. But it isn't just transformer. You have to add more to it. There's just many more things to it. But it's a very active area of research at this moment. In fact, we are getting to the point. In fact, if you remember, I did a paper reading a few weeks ago in which the neural networks were discovering results in mathematics undiscovered so far. It was actually making new discoveries. And that was the alpha geometry. Then there was this problem in which it literally beat the Olympiad level situation. And then there was this other situation where it was like, for example, the bin packing problem. How do you optimally pack things into bins? Where it outdid the best heuristics people had known till then. it actually discovered a better algorithm. So we are at the cusp of a very interesting world where you can, and there, map the creativity of an LLM with the discipline of a verifier to actually discover things. All right, guys. So with that, should we take a 15-minute break? And then I would like to talk a little bit more about fine-tuning and reveal one more reason fine-tuning matters. And then we'll take the afternoon break. Does that sound reasonable, guys? We'll take 15 minutes break. Okay.
That's